Hello, everybody. Hello again. Welcome back to session 32. It's definitely been an exciting session, hasn't it? Gotten a lot of response from you, and check your emails. And we will open our chat room tomorrow at 12 noon. Make sure to be around, and we will have a lot of fun writing some code and looking at the applications that come from this exercise. I really want to thank many of you for all your interest. The number of emails that I'm getting this time around has been fantastic. So thank you all. And remember that we have the commitment to put together our group strategy. Remember that we will have to develop a new product, and we want to have the right interfaces and the right tools for our potential or notional clients so that they could do their asset allocation and implement their strategies. So let's move on to some of the things that we've talked about in the past 20 minutes. So remember that we were writing a package to model knockout European call options. It is worth considering that we could do it either with closed form solutions for some processes. We saw the closed form solutions for a Vasicek model or for an arithmetic Brownian motion, and some affine models with jump processes. But nevertheless, we want to keep the world flexible. So we can do Monte Carlos and we can do binomial or trinomial trees. So here's the binomial tree world. So essentially in our previous hour, we went through step by step the process of developing this package. We defined initially a Black-Scholes binomial tree. Remember that we can customize our trees the way we want, but we will keep it simple, at least at this point. For your projects, remember we can go where, as it said, boldly go where no one has gone before, so remain creative. But nevertheless, here we will keep it simple. We have a Black-Scholes binomial tree, so the number of parameters that we need to model it is very parsimonious. So we have the interest rate, we have the dividend yield, we keep it at 0, the volatility parameter, which stands for standard deviation of the process, to 0.15. Number of periods 3, the number of nodes 50, and the hit barrier will be 100 for this exercise. For the number of nodes that we have for each one of the trajectories, this is how the tree will look like. Now, we know that a tree with these characteristics will be computationally extremely expensive because the number of trajectories that we will have for this tree is 2 to the n. So 2 to the 50 would be practically unmanageable for any reasonable computer power that we may have in our PCs. So as we implement our interface, we'll go down to a more simple exercise. So far, we will use this tree for only one node, one calculation of a barrier option. But as we want to build entire sequences of different options to produce graphs or schedules for different strike prices and different prices of the underlyings, then we will have to keep things simpler. So just to go back to our discussion of the last half an hour, here's the way in which we put together our package. The package has several commands. Here we have 7 commands, one procedure for indexing trajectories. This is key because we will have to have first an inventory of all the trajectories. Then in point B, we will separate those trajectories that have hit the barrier from those that are above the barrier before time to maturity. Then we will, on the third procedure, look at what happens at time t, capital T, which is the maturity time. So there may be some trajectories that survived all the barrier, but some of them will reach the final node out of the money. Then we will get a final calculation assigning probabilities to each one of the nodes of what will be the down and out call. And finally, we will build procedures to compare results with a plain vanilla tree. So now we'll go down all the way to our interface. So we have an interface where underlying each one of these nodes, so we will right-click just to highlight what we have behind each one of them. Here we have the code for that particular slider, and see that we will, first of all, we will use our package. This is the package that we ourselves developed. Congratulations to everybody. It's worth it, right? So we have the barrier binomial trees here, and we will use it. We will put the parameters, and then the machine will do all the calculations every time we click around here. So we will start with something truly simple. The number of nodes we parameterize between 1 and 10. Obviously, we can change our sliders parameters. Our barrier is going to be set with these sliders, and all the other components of the stochastic process are controlled by these sliders. So here's a tree. It's a very simple tree. And remember, I mean, I want to economize in computer time to keep things flowing as much as possible. And here we will have the payoff function at maturity. Here we have the value of plain vanilla valued for t, where t is the time interval between today and time of maturity. So I can have a call that matures in 2 and 3 and 4 or in 5 years. And the line in the middle, as we should expect, will be the barrier option. The value of the barrier option has to be lower, definitely, than the plain vanilla, which is shown here. And here we see some kinks, no? And this is normal for a binomial tree. And that's because small changes in prices, looking here, could put us on one side or another side of the barrier. And by doing that, we get these kinks. As we increase the number of nodes, which we will control here, the number of kinks will be lower, and it will look smoother. You can refer to previous chapter to get a sense of exactly what is going on. So we can play around now with these. We can move our process. Look at here. We can move our process higher. And by moving the process higher, obviously the price of our option is changing. If I increase the number of nodes, look at this, this gets smoother, and the number of nodes here also increases. We can play around also with time to maturity, and the price of the options both will increase. So we will use this in the following section to calculate credit spreads. And that's going to be very exciting. And we are going to compare that with the results that we got for the closed form solutions of well-known processes. So stay tuned. We'll be back in 2 minutes. Thank you very much to everybody.